I'm going to perform a one proportion z-test and interval for you. What I suggest you do before you watch my video is to actually attempt to do the one proportion z-test and interval by yourself. So I'm going to show you the problem, and then I'm going to have you go ahead and attempt to. If you have your packet, it's page 39, or if you don't, you can just look up 2005 number 4 on the AP Stats exams. All right, some boxes of a certain brand of cereal include the voucher for a free for a free video rental inside the box. Now I highlighted that because that's our context. The company makes a cereal claim that the voucher found to be 20% of the boxes. So that's going to be our P, our true proportion, what we believe to be true. However, on their experiences eating cereal at home, a group of students believes the proportion of the boxes is less than. So this is going to be right here, less than. That's what the students believe it's to be. So when I do my HA, that's going to be P less than 0.2. This group of students purchased 65 boxes. So that's going to be my N, number of boxes, of cereal to investigate the company's claim. The total vouchers were found were at 11, so that's going to be my X for a free videos in the 65 boxes. Suppose it's reasonable to assume the 65 boxes purchased of the students are a random sample of all boxes in the cereal. Based on this sample, is there support of the students' belief that the proportion of boxes of vouchers is less than 20%? Provide statistical evidence. When you see provide statistical evidence, that's telling you to do a hypothesis test. All right, so we're going to do a hypothesis test. And again, as I said, if you didn't do a hypothesis test yet, you should stop this video and try to do it yourself and then start it to show, to be able to see what you can do. I'm going to first of all start us off with the calculator, and then we're going to use the calculator to kind of keep going side to side. So the first thing I did was I wrote all of the things down that I'm going to need for this test. I have P is equal to 0.2. Remember, that's my true proportion that I believe to be true now. My P hat is 11 over 65. I broke it down into my X as successes, 11 successes over 65 total. And then I'm going to need my alpha when I'm rejecting or failing to reject my hypothesis at 0.05. And then I'm going to need that my alternative hypothesis is going to be a less than. So let's jump over to our calculator. And I'm going to go to, from your calculator, you can do a calculator page, or you can do it from the spreadsheet. If you do it from a spreadsheet, it actually will bring up a nice little graph for you when you do it. So I'll just do it from the spreadsheet. But I'm going to go menu, stats, test, and this is a one prop z test. So I'm going to do PO, that's the null hypothesis because it's HO. PO is just your null hypothesis, P, which is 0.2. The successes that we have is 11 and at a 65. And then my alternative hypothesis is less than, because that's what we were, and then I can hit draw. And I have everything already here. So I've got all my answers here. I've got my p-value, my z-score, and everything. And we'll just kind of keep going back and forth to this to be able to use my conclusion. Now, I've already written it all out on mine, but you can see we already have z is going to be negative 0.62. My p-value is 0.26. My p-hat is 0.169, which we already calculated, and my n is 65. Okay, so back to here. So I have that on my calculator, and I'm looking at it on my calculator as I'm doing my phantoms. Okay, so my phantoms, the first thing is my parameter, and I have to write it out in context. So if you notice what I highlighted in gray, I just pretty much wrote and pictured it right here. I just copied it. The true proportion of vouchers for a free video rental inside the box of a certain brand of cereal. Because remember, I'm sampling the cereal boxes. In fact, it tells you a random sample of all the boxes. So that kind of also gives you a hint. That's what your true proportion is whatever I'm doing my random sample of. I just want to know what proportion has vouchers in it. Okay, so my hypothesis, my HO is P is equal to 0.2. Your HO is always P equals. And then it's 0.2 is the That is what is believed to be true historically of the boxes of cereal. That's what they set their machines to do, is to put it into 20%. And then my HA, or my alternative hypothesis, is what I'm trying to show, what the students believe to be true. So the students believe that it's less than 20%. And it's always compared to the 20%. You don't put your actual value. That's your p hat, and that comes in later. So my conditions, my assumptions and conditions are the acronym RILT. Random sample given. Just don't write random sample. Make sure that you just say it's given or done or completed or something like that. Now, independence, the way to show independence is showing my random sample and showing my large sample size. So really, I'm explaining it. Each independent box is independent from the next. How do I know that? Because I have a random sample and I have an NP-NQ. Now, this is NP-NQ, which is 20%. That is my P. And my N is 65 and 80%. And my Q is 80% because it's the opposite of 20. And both of those are greater than 10. This shows me that I can do my normal model. Now, the last one is my sample size has to be less than 10% so that I can do my standard deviation of square root of NP, or excuse me, square root of N, yes, and PQ over N. So I'm checking, and certainly 650 boxes is going to be less than all of the boxes that I have there. So it shows that I have less than 10%. Okay, so you're going to name your test next. And the first of all you're going to do before you name your test is say, look, I've checked the conditions so I can proceed to the normal model. And in the normal model, I have a test called the one proportion Z test. Z is on a normal model. It's my standardized test statistic. So I'm going to go ahead and proceed to it. My test statistic shows I have 11 over 65 minus 0.2, and then my standard deviation. That comes from your formula chart, which I'm going to look up here for you in a second, but the formula chart has p hat minus p over square root of pq over n, and this is on the back side of your formula chart in the top right-hand corner, and you can go ahead and see under a one proportion sampling distribution, and you will see it under your standard deviation. One thing I want to point out is this will match with this. Because it is a model that is around your parameter, and you are trying to see if the p hat measures in your parameter. So I think it's easier to do the z-score, but you are welcome to do a model that's around 0.2, and then you would do your 11 over 65, which is 0.169, and you would do that. And you could go ahead and make a model there, and you are welcome to that, but you are going to get the same p-value of 0.2676. So remember back here, I got the p-value at 0.7626. You can see, yes, 0.2676. Is that what I said? I don't know why I'm saying it backwards. 0.2676. I'm saying it backwards, but that's the p-value. You can do it this way, or you could do a normal model, normal CDF. It's just a little easier to do the test the way I showed you. Okay, so you're required to do either a picture labeling normal model here, or the picture labeling the normal model like this, 0.2, which this is 0.2, 0.8 over 65. You are welcome, but it's going to give you the exact same answer. Remember, the model is based on my population, and I'm seeing if my p-hat, how often my p-hat exists on my normal model. And if it barely exists, it's like, wow, what this is saying is if this does not exist in a large percentage of time, this little area that we have here is the percentage of time that my sample, 11 out of 65, happens by chance. And if it doesn't happen by chance very much, we're saying, wow, that's pretty significant. We need to look at our original model and potentially change it. But if it happens by chance, we're like, hey, that's just due to sampling variation. I know I said 20%, but 16% is due to sampling variation because sometimes it's not exactly 20%. It might be over and it might be under, and we're used to that, and that's not something out of the ordinary. So we did find that it's not out of the ordinary because our p-value does, in fact, equal something that is greater than 5%. So we make our decision, since p-value is equal to this, which is greater than alpha, we're going to fail to reject our hypothesis. And our hypothesis should be an equal sign there. And our hypothesis is that the proportion of vouchers is equal to 20%. Then you're going to state the conclusion. Since I failed to reject it, I have to say I don't have convincing evidence to say that it's less than. So the students do not have convincing evidence to say that their 16% of their sample, their vouchers, is statistically significant. We know that 16% is less than 20%, but we're saying that's due to sampling variation, that sometimes you're going to get it lower, sometimes you're going to get it higher, and it's within a normal realm of error, so that we don't say it's so unusual that it shouldn't happen, okay? So let's jump then to a confidence interval. Now, guys, you stop here if this was your problem on the AP test. However, just for demonstration purposes, I'm going to do a confidence interval. If you could run the confidence interval that corresponds with this hypothesis test, stop the video, try it on your own, and then start it. Okay, if you run a confidence interval, you are going to run a 90% confidence interval because it corresponds to my 5% alpha. The reason I know it's 90% is because if I draw a model and I see this is the 5% that I'm doing as my rejection, that's my 5% level, and I know anything less than 5% would get rejected because that's my alpha that I have chosen to use right here. And since it's one-sided, and so I put 5% on this side, 5% on that side, then 90% is left in the middle, and that means that's the confidence interval that I'm using because the confidence interval is always the center percent around my mean. Okay, so we're going to do a 90% confidence interval. So the first thing I'm going to do is, just like I did before, is I'm going to go ahead and run that confidence interval. For that information, I need to know what my X is, my N is, and what level of confidence. So I'm going to jump over to my calculator. I'll do it from a spreadsheet again if we want. And if I go, or you can do it from a calculator page, a blank page, it doesn't matter. So I'm going to go stat confidence interval and a 1 prop z interval. For this one, remember I had 11 out of 65. My confidence level was 90%. Okay, and there we go. So I'm going to be using this data in just a bit. So I've got my confidence interval is going from 9.27% to 24.57%. Look at there, my p hat is 0.169, which we know already because 11 over 65. And then my margin of error is given to me at 0.0764. Okay, so I've got that information on the side, and I'll keep referring to it as I need it. So I'm going to run panic. And if you notice, panic is the same as above in the hypothesis test. So this here is just identical to what I just wrote above. So my assumptions and conditions are identical. So random sample given, independence the same, this is the same. The only thing that's different is this one here. The L is different. Above, in this L, I used NP, NQ, because the model was about my population. That's what the model is built on. However, in the confidence interval, the model is about my p hat. The model is built around p hat, so I have to use NP hat. That's p hat. Oops. And that's q hat. Where before, of course, I used p and q. So that's the only thing that's different, but everything else is identical to the hypothesis test so far. So now the rest is what's a little different. And so the N in panic means name the interval, and this is a 1 proportion z interval, where of course before it was a 1 proportion z test. And now we're going to find the interval. Now this interval equation is absolutely on your formula chart that you're allowed on the AP test. but it is p hat plus or minus critical value p hat q hat over n. Now you kind of have to piece it together because on the front page it gives you confidence interval is equal to statistic plus or minus critical value times standard error of the statistic. And then on the back page, it gives you the standard error of the statistic. And then, of course, it says statistic. For critical value, I'll show you how to do, because this one, you saw how I got this interval just a second ago on the calculator. And that's all you have to do is you're going to put these values in here for your work, and then you're going to write this one down here from the calculator. Now, to be able to get the 1.645, your calculator doesn't give you that. Be able to get the z-star, the calculator, does give you that, but not the confidence interval. That doesn't give you that. The calculator for z-star for 90%, the way you're going to find that is inverse norm, and you're going to put area 95%. The reason you're going to do 95% is because your calculator doesn't know you're doing the center 90%. And if you put in 90% on the calculator for the inverse norm, it'll stop you somewhere around here and it'll give you this value. And I need this value right here. So I have to kind of trick the calculator and make sure, because it starts from here, I have to go past that 5% all the way to this percent here. So I have to do this 5% and this 90%. So that's a total of 95%. So when I'm doing the inverse norm, I have to put in 95%, mean of 0, standard deviation 1, and that gets me 1.645. Now, when I'm putting it in, when you saw me put it in here on my confidence level, here, notice when I put it in, I just put in 90 because it's literally asking me for my confidence level, which is 90%. Inverse norm doesn't ask you for your confidence level, so it doesn't know that I'm trying to find the center 90%. The confidence interval calculator understands that, and it's already programmed to do that, so that's why you just put in the actual confidence level. Okay, and everything else you're already found, which is the p hat, and of course, that's p hat and q hat, and then of course this is your n. So all these things here, you already have been, you've already found. So now your conclusion. We are 90% confident that the true proportion of vouchers for a free video rental inside the box of a certain brand of cereal is contained in the interval 9.27% to 24.57%. Okay. That's how you find phantoms, and that's how you find panic. Now let me talk about what they mean and how they connect. So if you notice, my true proportion way back in the problem was P is equal to 20%. It says 20% of the boxes. What that means is I made, or not me, but the owner of the machines, the manager of the machines, or whoever programmed the machines, programmed to put 20% of the boxes to have vouchers in them. So that's what we believe to be true. So we found that since 20% is actually contained inside the intervals, that it is. And we were 90% confident that it would contain it because that was my conclusion. Well, we indeed found that absolutely yes, it did. So what does that mean? Let's connect it to our hypothesis test. Well, the decision with the hypothesis test was that we failed to reject Ho. We said we did not have convincing evidence for Ha. We failed to reject, what are we failing to reject? We failing to reject that the proportion was equal to 20%. So we didn't reject that. They were trying to reject it. They were trying to say, no, that's not true. But we said, erase. Yes, it does seem to be true. The evidence for Ha of P less than 20% is what we said we could not reject. We could not reject that it's equal to 20%. We could not say that indeed it was less than 20%. So basically we said we kept the status quo that we do believe that 20% would be contained in the interval. Wait a minute, what? Yes, it was. It indeed was contained in the interval. In fact, 20% was contained in that 90% confidence interval that we did. So if we fail to reject then we would expect our interval that we created to contain my 20%, my status quo. There's no change, okay? Let me give you one more scenario. Let's say I had a p-value of 0.025, right? So obviously that's less than 5%, and we would reject. Let's do our same one, that p is equal to 0.2. If we did then I would expect to see my confidence interval, instead of being something like 9%, I would expect it to be maybe 0.25 or to, let's say, 0.372. So 25.4% to 37.2%. So what I'm saying is if I actually rejected where I rejected then I would expect, see there's 20%, my confidence interval to not contain my proportion. And we would say, oh, it didn't contain that, we need a change because my true proportion is not contained in there. Same thing with here. Ooh, we had a low p-value, we reject this. We need a change. Which we're saying we're going with, is that change, okay? This is not what we came up with. We came up that we failed to reject, so it was in the interval. However, if we did come up with a p-value that was low and we say, hey, we're rejecting, then we're saying, ooh, there needs to be a change. There needs to be a change. And there's my change that I'm suggesting. And so same thing here is if my 20%, my original population is not in the interval, we're saying there needs to be a change because this is what we expect status quo to be. All right, I hope that helped you. I also have another video for a two-proportion z-test and interval. All right, reach out to me if you have any questions and have a wonderful day.